My name is Amarsin Gowande, and this is a video presentation on Majorana fermions in quantum computation. A Majorana fermion is a fermion that is its own antiparticle. They were first theorized by Ettore Majorana in his 1937 paper, A Symmetric Theory of Electrons and Positrons, which suggested that neutral spin 1/2 particles could be described by a real wave equation, his Majorana equation. The equation was similar to Dirac's equation, apart from its use of charge conjugate psi c. The use of both psi c and psi meant that the field psi could not be coupled to a charged electromagnetic field without violating charge conservation. Therefore, the field psi must be neutral. These neutral spin 1/2 particles would be their own antiparticles, because the wave equations of particles and their antiparticles are related via complex conjugation. For a particle to be its own antiparticle, it must be a truly neutral particle. That is, all its charges must be zero. This requires not just that the particle be electrically neutral, but that its other algebraic properties, like magnetic moment and color charge, must be zero as well. Particles with integer spins have been found to be truly neutral. Familiar examples include photons of spin 1, neutral pions of spin 0, and gravitons of spin 2. However, no known fermions are their own antiparticle. Majorana suggested that the neutron could be such a fermion, but we now know that that isn't the case. Despite being electrically neutral, it is not its own antiparticle because of its non-null magnetic moment. Majorana also speculated that neutrinos, then purely hypothetical particles, could be truly neutral fermions. However, once they were discovered in 1956, their observed properties seemed to undermine this idea. Namely, there seemed to be a strong distinction between neutrinos and antineutrinos. However, this distinction in recent years has become fuzzier, as it was discovered that the flavor of neutrinos can actually oscillate. An electron antineutrino emitted from the sun could arrive at Earth as a muon antineutrino. Let's investigate the math of Majorana's a bit further. The creation and annihilation operators can be written in terms of gamma operators. For the case of electrons, the creation operator corresponds to the creation of an electron, and the annihilation operator corresponds to the creation of an electron hole. These are the standard fermionic operators. In this case, the gamma operators are our Majorana fermion operators. Gamma 1 and gamma 2 are real numbers here, and they can be expressed in terms of the creation and annihilation operators. In fact, they are an equal superposition of creation and annihilation, an electron and a hole. Complex conjugating these expressions reveals the identity gamma dagger equals gamma. So can we create or observe these particles in a real sample? Let's perhaps consider a bound state of an electron and a hole, an exciton. These are found in semiconductors by exciting an electron over the band gap, creating a missing electron in the valence band and an extra electron in the conduction band. Is this a Majorana fermion? No, it is a bound state of two fermions, a hole and an electron, and is therefore a boson. Instead of a bound state of both an electron and a hole, we must consider a superposition. A better place to search for Majoranas is in superconductors. In superconductors, we have many of these Cooper pairs of electrons. These Cooper pairs form a condensate in which the number of Cooper pairs is not a conserved or well-defined quantity. We can have a hole and a Cooper pair together essentially be the same thing as an electron. It costs nothing and is immeasurable to give one Cooper pair to this process. We can say that in a superconductor there are only two states, one in which there is an integer number of Cooper pairs and one in which there is an extra one electron in an excited state. Adding another electron or hole to the superconductor will create another Cooper pair, which will be added to the concentrate. The particle-hole symmetry of the superconductor leads to the equation gamma dagger E equals gamma negative E. Only at energy E equals 0 does our identity of gamma dagger equals gamma prove true. Therefore, our Majorana must be found at energy E equals 0. This binding to energy E equals 0 is why Majorana fermions are often called Majorana bound states. When they arise in superconductors, Majorana fermions come in pairs. This is because it takes two of them to form an ordinary fermion. These Majoranas could potentially even be separated spatially. With ordinary fermions, we can encode these qubits in a local way, using properties like charge. An empty state may correspond to state 0 and a filled state to state 1. As superpositions of electrons and holes, Majoranas can be similarly encoded as qubits, but in a non-local way because of potential spatial separation. This turns out to be Majorana's qubits' greatest strength. A major issue with encoding fermionic states as qubits is that they must be encoded locally. They are very sensitive to local perturbations, and their decoherence time can suffer as a result. Majoranas, however, can be encoded non-locally. On a local level, these two Majorana states look the same, only differing in their collective view of the system. This effectively hides the physical state of the qubit from the environment, protecting them from local perturbations. As a result, Majorana qubits are expected to have a very high coherence time. We know that superpositions of electrons and holes exist in superconductors, but they are often quickly destroyed by quantum fluctuations. In 2008, Liang Fu and Penn's own professor Charles Kane predicted in a breakthrough paper that the proximity effect between an S-wave superconductor and the surface states of a strong topological insulator result in a state that could theoretically support Majorana bound states. Fu and Kane also suggest that a linear superconductor topological insulator superconductor STIS junction could form a wire for Majorana fermions. These junctions could be combined into circuits, allowing the creation and manipulation of Majorana bound states. The first experiment that showed signatures of Majorana fermions was performed by Murik et al. In 2012. The schematic of the device setup is shown on the left, and an SEM image of the device is shown on the right. The experimenters first fabricated a pattern of narrow and wider gates in a silicon substrate. The gates are covered before indium antimony nanowires are deposited. The nanowires are electrically contacted with a lower and upper contact, that is, either a normal or superconducting material in different variations. To perform the spectroscopy, we create a tunnel barrier in the nanowire by applying a negative voltage to the narrow gate. So what are we looking for? Majoranas, despite having neutral charges, are still detectable. We are here looking to reveal a state of zero energy through tunneling spectroscopy from the normal conductor to the end of the wire. The zero energy peaks should rigidly stick to zero energy, while the magnetic field and gate voltages are changed over large ranges. The zero bias peak should also become absent if we take out any necessary ingredients for Majorana bound states. The results of the experiment satisfied these requirements, showing that the zero bias peak remains at zero through a range of 0.07 teslas to 1 tesla and through a wide range of voltages. The zero bias peak vanishes when the superconductor is replaced with a normal conductor. Thus, The researchers concluded that the spectroscopy provides evidence of Majorana fermions. A recent paper published by Wang et al. In 2018 suggests that iron-based superconductors have promise as a platform for realizing and manipulating Majorana bound states at relatively high temperatures. An iron-tellurium-selenium bulk superconductor is used with a superconductor transition temperature of 14.5 Kelvin. A high-resolution tunneling spectroscopy experiment is performed. Similar requirements as the 2012 Mauric experiment are made and fulfilled. The researchers here found that the zero-bias peaks vanish at around 3 Kelvin, which is a much higher temperature than many previous Majorana platforms. Majorana qubits have not yet been developed experimentally. An article published by Eisen et al. In 2016 proposes several geometries for Majorana fermions based on quantum computation. There are two main proposals for the geometries, a double superconductor and a tri-junction geometry of superconductors. In the diagram, the black lines, either open or closed, indicate gate valves and the X's indicate where Majorana fermions would form. The tri-junction geometry is favored because it can enable easy exchange of Majoranas and thus enable braiding. Braiding is a theoretical qubit operation of Majorana fermions where the pairs of Majoranas could exchange places to encode information, forming braids. This could lead to fault-tolerant quantum computation and is another promising aspect of Majorana fermion-based quantum computation. There is still much to be done in the field of Majorana research before effective quantum computers can be designed. Majorana qubits cannot yet be experimentally compared to other competing qubits because of the lack of experimental research. Although certain researchers have been able to detect signatures of Majoranas, an established detection scheme for Majoranas has yet to be developed. Experiments to test the coherence time, measurement fidelity, and dephasing time have not yet been developed. Majoranas hold incredible promise in the field of quantum computing, but a lot more experimental research must still be done. Nonetheless, it is an exciting time for Majoranas. And lastly, I have some references here that if you're interested in learning more, I recommend going through. There are some video lectures as well, and the links contained here that were particularly insightful for me. Thank you.